Okay, this is Elliot, and today I'm going to talk about visual odometry. And then what you're looking at here is the visual odometry algorithm. It does not depend on GPS signal to estimate its position, but instead, only by looking at this sequence of images in real time. It doesn't have to be real time, even if it is recorded video. Only by looking at this video stream, the algorithm is estimating the velocity on the right-hand side, and then it just integrate this velocity, and then it will have x, y, z position, and then I'm just plotting all this in a different view by z versus x graph, and then it just looks like a kind of map view in real time as you move your camera on this path, and then you can actually estimate your position only based on these images without any GPS. So that's the visual odometry. And then in this project, I'm using the convolutional neural network. And I was curious if the neural network can estimate all this all at the same time, end-to-end method. And especially if you're coming from this GitHub repo of this visual-inertial odometry, I just wanted to give a little bit more instruction how you can run this on your end without too much of a trouble. I wanted to go over this in this video. So let's just get started. Before we dive in, let's just talk about just traditional method of visual odometry, which comes with all these kind of detailed steps to go through. For example, we need to look at this camera. This is default raw camera, and then usually the camera comes with this distortion. And then as you can see, all these flat, actually this is a bookshelf, and then this wall of the bookshelf is not supposed to be curved like this, but it's curved. We need to rectify this image, and as you can see, everything is curved, and there is a barrel distortion on this image. And then after rectification algorithm of the computer vision, and then you can see all this checkerboard is all rectified, all flat edges over here. So that's the first step of the traditional method of visual odometry. And then there's second step to extract the features. So this top image is from the left camera. There are two cameras involved, and then this is image from the right camera. And the difference is that if you look at this wall of this fence, their position is different, and that's because one is on the left, one is on the right image. So there are two images, and then first thing you need to work on for the left-hand side image is actually for both images, just extract the features like this. These all blue dots are the features of the image, which is significant pixel-wise difference that you can detect. It could be detecting corners and color-wise difference or edges and all that. So anything that kind of could be significant point can be features. And there are several feature detection algorithms in OpenCV. I will not go over all the details of the feature extraction, but for now, I just wanted to say these are the feature, and feature extraction step is required to go over this feature extraction here to go over the visual odometry. And that's because we want to match all these features on the right-hand side as well. And this green line is the correspondence of these features on the left and right hand side images. And the reason why we do that is because we want to create 3D point cloud using epipolar geometry of this stereo camera, like two images, and then you can actually backtrack all these actual 3D point of all these features in the images, and then we want to create 3D point cloud for these features. Now, if you actually map all these 3D point clouds, it's going to be looking like this in a way in 3D point. And then you need to estimate frame to frame, you will have all these point cloud, one frame, and then after 0.03 seconds, for example, if it is 30 FPS camera, then you will have two different point clouds, but they're actually the same point cloud of the same object, but their position and then rotation is a little bit different. And then this kind of point cloud is evenly distributed on most, so it's quite difficult for me to make a point. But now let's assume here the simplified version of the scene, and then this is a point cloud from sphere on frame 1 and then frame 2, like after 0.03 second. And let's assume this scene is stationary. Only moving thing in this situation is the camera itself. You have this object and then point cloud extracted from this scene, and then it somehow look like this. And then after 0.03 second later, you take a picture and then extracted all these point cloud and built all these point cloud. And then it looked like this. It's like 45 angles rotated. It means your camera is actually opposite direction rotated to 45 degree, like negative 45 degree. And that's how you can figure out how much your camera has moved between two frames. It's 45 degree rotated. It means your camera is negative 45 degree moved. That's the ego motion of the camera. And then to solve this, to actually figure out what is the actual angle that's best fit all these points in this 3D, there are like a lot of nonlinear optimization algorithms like iterative closest point and so on. And they are using all this optimization method. If you figure out the angle and then displacement of all these point cloud, and then you just integrate it frame by frame, then you will have all these estimated path like this. That's what it is doing in real time in the for loop. So let me switch a gear a little bit, and then there's another concept in computer vision, and that's called optical flow. Optical flow is like this. So given the image and on the left-hand side, left camera, this monocular camera is fine. And then you take another image at next frame. And as you can see, the fence over here is moved. It means your camera is actually moving forward. And then if you just calculate the difference between the pixels between these two images, and then you can actually measure the movement of the pixel because you can match the pixels, right? Like feature extraction, feature matching algorithm. And then you can estimate the movement of this pixel in 2D, and then it's dispersing left top, left bottom, bottom, and so on. And this region is not good. Let's not use this kind of information if it is real-time algorithm because it's so noisy. However, if you look at all the rest of the area, this optical flow is quite consistent so that you can conclude that this camera is moving forward. And then people have been playing with this optical flow, and then they just put everything into this convolutional neural network to estimate this optical flow. And then what they are doing is they are just feeding this raw image without considering rectification of the image or camera calibration. No, nothing. They just feed the raw image into the convolutional neural network, and then the convolutional neural network is estimating the optical flow like this. And this is just a color-coded vector in 2D, like blue one is moving left top, greenish pixels are like moving left bottom, red is moving to the right side. So that's the optical flow. You're just literally feeding this image information into the convolutional neural network, and you don't need to do any sort of calculation like optimizations, no nothing. So that's really a great thing about this convolutional neural network. And then later on, people are just playing with this neural network, not just to estimate optical flow, then instead they are just like estimating the camera ego motion, like X, Y, Z information of the camera displacement in real time. And then again, this is the deep learning based approach. So they don't really need to work on camera calibration, feature extraction, no nothing. Just literally just feed all this information at time t and t+1 and so on. And then they are just mixing with this information from IMU. IMU is the inertial measurement unit. It gives us any inertial information. What is the acceleration? What's the angular velocities and so on. And then they are just mixing it to estimate the position of your our camera and so on. And then this paper is actually, I was really mesmerized with this paper because what it does is just like ChatGPT. When you train the ChatGPT, large language model, you just throw all this information with the right structure of the convolutional neural network plus recurrent neural network together, then it will just directly estimate the position. When it comes to large language model, there's a deep learning structure called attention mechanism. In this version, RNN is doing the similar thing, like long short-term memories and so on. Again, you don't, in theory, you don't really need to do any sort of complicated calculation to estimate the camera ego motion. And then these people are just fusing all this information and then wrapping all this information with the extended Kalman filter to estimate all this. I wanted to replicate all this thing, so that's why I end up with this project. So the difference with this, my project and this project, is that they are only feeding the IMU value after the CNN, but I wanted to feed the rotational information within this CNN sort of thing. I just wanted to estimate all this together. To do that, we need to talk about rotation matrix, but I will skip for now for detail for now, because assuming that if you are coming from this GitHub repo, you're already familiar with this rotation matrix, and other things like detailed computer vision and then 3D transformation matrix as well. But however, if you are really curious and if you want me to go over all these theoretical things, please comment down below. I will go over them in a separate video, because I just want to focus on for you so that you can have this project working on your side. So that's my purpose of this video. One thing I still wanted to mention is this part. So we have this robot, this kind of robot, and heading towards the north. And then at the next time frame, we measure this robot is moving to this heading to the east side, and then it moved from 0,0 to 0,1. And then the interesting thing about this nonlinear movement is that it's called twist motion or screw motion. It's not because the concept is screw or twist or something, but it literally resembles the motion of the screw itself, like rotation and then the translation movement are happening together. And then this is the angular velocity, and then this is the translational movement of the vector. And the interesting thing is it's not 0,1. For example, if it is translational movement, it's more 45-degree movement, and then rotation is happening together. And then it will end up with 0,1. Rotational information is about pi over 2. That's the angular velocity. And then this is the linear velocity. And then I think it's interesting that it's not 0,1, although you end up with 0,1. And that's because of this screw motion, like rotation and then translation movement happens. They are happening all at the same time. But we can't just simply integrate all these because of a nonlinear phenomenon of all these things. And then to be able to incorporate all this nonlinear motion, we need to use the concept of exponential mapping. And then this is a little overwhelming math, but anyway, the only point I wanted to mention is that I'm using all this information separately so that the neural network can output this, and this. Now, I wanted to also go over the basics of the Kitty data set. And it has, if I look at, for example, this Kitty data set position data. So if I just open up this position, it has 12 columns. And that's because it's a transformation matrix. And then 3 by 4, this transformation matrix usually come with 4 by 4. And then this Kitty data set has 12 columns, and that's because first 3 rows and then 4 columns. And that's going to be 12 columns here. And then the last row here is all 0, 0, 1 all the time. So we can just rebuild this 1 by 12 into 3 by 4, and then we can just pad all 0, 0, 0, 1. Then we can still keep the 3 by 4 matrix here to be able to build finally 4 by 4 matrix at the end. So that's the ground truth value that we'll be using to train this Kitty dataset based visual odometry. And then another interesting thing about the project, not just this project actually, is this idea of this sort of semi-unsupervised learning is coming from this paper. I think if you are in the research field, you are very familiar with this paper as well. Now you have position ground truth, so you can always calculate the loss. After calculating feed forwarding this neural network, you can always calculate the loss by comparing your prediction and then ground truth. And if I only use, that's going to be a Euclidean distance, x minus mu squared, and then if you take a square root of all this, that's the Euclidean distance. However, if I use Mahalanobis distance like this one, then we need the information of the covariance matrix, but we do not have any covariance matrix related information in Kitty dataset, right? However, we don't really need it if we want to calculate Mahalanobis distance. For example, let's say after actually taking derivative on all, that's our loss function. Okay, I'm really bad at drawing the lines. So that's the optimization function or loss function that you will actually calculate. And then say, if this covariance matrix is too large, this loss will go up. However, if it is too small, again, because it's on the denominator side, if it is too small, again, the loss will go up. In the neural network, during the calculation, it should be able to figure out the best covariance values based on the training. So what do I mean by that, right? There's no covariance matrix as a ground truth. It doesn't matter, actually. At the very early stage of the training, the neural network will output a random value for this, say. And then if it is too large, it will optimize the neural network to reduce this one, the covariance matrix. But now, covariance matrix. If the covariance matrix, again, is too small, this Mahalanobis distance will blow up. Then the neural network, again, need to reduce the output of the covariance matrix. So in that direction, this neural network will be optimized. The weight vectors of the neural network will be optimized to reduce this covariance matrix. And then this term will try to reduce as well. Or actually, this one will try to increase this covariance matrix because it's on the denominator. So they are fighting with each other to optimize the best covariance for this Mahalanobis distance-based loss function. That's the basic idea of guessing the covariance matrix. Another thing that we need to note is this part, the Cholesky decomposition of the covariance matrix. Covariance matrix is 3x3 matrix with 9 elements. But if I let the neural network output 1x9 vector, it's just too many values. If we can reduce the number of outputs, it will actually, we are literally reducing the number of the permutation for the neural network to guess. Also, the neural network doesn't know about the property of the covariance matrix. For example, like semi-positive definite function. And then we will come up with the mathematical property as a loss function of the covariance matrix, right? But we don't have that loss function here. Instead of letting the neural network directly putting the covariance matrix, we will let this neural network output Cholesky decomposed version of the covariance matrix, 6 elements of this, and then they can be whatever number, because by definition, Cholesky decomposition will anyway construct the regular proper covariance matrix using this. This part will be done manually. And then finally, we can calculate the Mahalanobis distance. That's the idea from this paper. And I'm using this same idea on my project as well. And then the only difference is that I'm feeding all this rotation information alongside with the convolutional neural network. So at the same time, convolutional neural network is processing my image and then kind of amalgamating all this information from this gyroscope, which is angular velocity information, alongside with this fully connected layer or multi-layer perceptron to process du, dw, and the translation. And then, like I said, du, actually this d omega. So this linear translational movement, linear rotation movement. And then I'm just using exponential mapping to estimate the translation in body frame. And then again, I use rotation matrix to rotate every information, this dvu, xyz, frame to frame displacement into a ground frame using the rotation matrix. If I run this algorithm, it's going to be like this. The input images, 2 images are like this. They are standardized grayscale images, and then they are running all this information in real time. The frequency is really low, and that's because it's plotting algorithms. As you can see, this car is turning to the right, and then it's estimating the path of this camera. The problem is just too slow, and actually it's not really the algorithm itself, but it's actually the matplotlib's plotting algorithm in real time. So if I don't plot at all, if I don't plot this, it's going to be pretty fast, like about 60-ish frame rate to estimate the position of this visual-odometry algorithm. So that's the demo of this project. And then this project doesn't actually by default only assume kitty data set. I have tested AirSim by Microsoft. I'm just feeding all these images frame by frame, and then it's very easy to collect this position information because from the simulation and there's no noise in the image. It's really convenient to train one by yourself. And then this is the result of AirSim based visual odometry. And then the drone is moving forward and turn left. Then the red one is the ground truth signal. And then blue is the estimate predicted movement. And then this green ellipse is the uncertainty of your camera. So it estimates uncertainty. And then, like I said, this deep learning based method doesn't require any sort of image rectification or camera calibration, no nothing. You just train, say, with the barrel distorted images, and then you just also feed the barrel distorted images. You just need to be consistent, and it will just estimate the camera motion as you designed. And it's not limited to any sort of RGB images. You can just feed the segmented images or edge filtered images as well. Because what the convolutional network is trained is not really anything like color or edge or features. Instead, it's more like a texture, pattern of the texture of the scene. So that's what the convolutional neural network is being trained for. And then instead of using LSTM, I found this Kalman filter is way better. I wouldn't say way better, but it's way more cost-effective compared to using LSTM. What I mean by that is this. So this guy is using RNN, but I'm not using RNN here, but after this convolutional neural network. And then instead, I'm just using Kalman filter algorithm. And then what I'm just doing is I'm just using the linear acceleration information from IMU. And then there is a process noise for the acceleration, but instead of using the process noise of accelerometer data itself, instead guess all these noise information as a covariance matrix, and then just process whatever at the beginning. And then you will have a lot of error like this if there's random noise here. And then after iterating all this entire path, then calculate the position-wise root mean square, and then feed that information to this uncertainty optimization neural network. And then it will output a better covariance matrix for entire data set or training data set. And then I'm just using that information again to tune or optimize the Kalman filter algorithm here. And then this is the result here. So this red is again ground truth, and then blue is a CNN only algorithm. And then green signal here is the Kalman filter output of this position. The difference between this previous paper and this one is that, as you can see, using RNN or LSTM or whatever type of RNN, it's really good. I should say that it's really good. Although the computational resources to train is really tremendous and overwhelming, but it is really good. But what's not good about it is that, anyway, it's not perfect. And then the rotation information is messed up. And I think that's expected because it doesn't use any information like IMU. And then in this result, I am using IMU, Inertial Measurement Unit. And then it is expected that there's no rotation-wise confusion. Still, the difference is the translational or drift error of this path like this compared to the ground truth. And then anyway, I believe this is one of the best results. In this graph, it doesn't show a lot of drift in the position. Anyway, this convolutional neural network will output the result with the drift anyway. Then why don't we use just Kalman filter because it's cheaper than RNN in practice. That's my argument for this project, but still, I do have mixed feeling about this approach, in general, using the convolutional neural network for the visual odometry. And this is another example that I collected my own data using my IMU based on Pixel Autopilot and then my stereo camera. And then I just drove around my apartment community in the US, and then this is the result. And after Kalman filter, this is one of the best result in green line, the Kalman filter output. But the interesting thing is whenever you train in different data set, doesn't even always like converge like this. Sometimes it's just like random, this almost like random distributed position out there, and this is one of the best result. And the result always different by training time, and I'm pretty sure that's because of lacking the training data set. If I have more training data set, the result will be more consistent. In general, is this a good approach? I don't know. Like I said, I do have mixed feeling. Instead of using end-to-end manner, we can just use deep learning for the feature matching, and then create the point cloud using the good old-fashioned method, and then mix with IMU data, and then estimate the positional velocity of your camera. I think that might be better, but I don't know. Because I'm actually this is what I was thinking before ChatGPT came out. And then this sort of end-to-end method, no traditional algorithms required. And then this might still work, because if you can train a lot of data with a lot of amount of time, with a lot of cache as well, then this will just work, probably, as much as ChatGPT is working fine these days. So I don't know which is right direction, just end-to-end deep learning method for visual odometry, or mixture of the deep learning with the traditional method. I don't know. You tell me. Please comment down below how you think. Okay, so let's go over the code of this GitHub repo. So I just cloned it first, and then when you clone it, just make sure where you need to clone all this sub project as well. And I think I have the cloning code here. So that's the recursive tag there. So make sure that you need to recursive git clone here, because there's a sub-project called my PyTorch API, which is literally just my own convenient functions to create the convolutional neural networks and so on. So that's the only catch, and then just clone this, and then you'll have this. And then this repo just assumes Docker and Docker container, Docker compose environment based on NVIDIA GPU drivers. First of all, you need to make sure you have NVIDIA driver is working on your side. For example, if I just open up a terminal and if I type NVIDIA SMI, and then it shows the list of all the GPUs on my system like this. So I have 3 GPUs on my computer, so that's why I have 3 GPU list here. So it means there's a NVIDIA GPU driver that understands this command. So that's one of the command that you can test if you have proper GPU driver for the NVIDIA GPU card. So that's that, and then make sure you need to install Docker and Docker Compose. And then on top of that, finally, we need to install NVIDIA Container Toolkit so that the Docker container can access the GPU resources from your host machine, and that's NVIDIA Container Toolkit. And then I have just put some commands to install NVIDIA Container Toolkits like this, so make sure you install this on your host machine first. And then finally, you can create Docker container using Docker file here. And I'm just relying this PyTorch CUDA version from the official Docker Hub. And I'm just adding some Python packages like this, using these packages mainly. So that's the Docker file. And then another important thing is this volume and deploy, by the way. So deploy is this actually the part of the Docker Compose that let your container access the GPU resources. And then volumes are like this src, which is actually all the Python code of this project. Now, another important thing is this part. So I'm mounting all these KITTI data set into this path of the Docker container. So if I actually go to this path on my host machine, that's the tree structure of my folder, and then I put all this Kitty Odometry data set in this format. So make sure you have the same feature. Actually, I didn't do anything. I just unzipped all this Kitty data set, and then they come with this kind of folder structure. So that's it. So just to make sure, put your own Kitty dataset path here for the bind mount of the Docker. And if you're not sure about the bind mount and Docker Compose, all that, I have a short video list for Docker. So I'll put the link in the description. So refer to that about the Docker. And then that's it. Just simply run Docker Compose -d to detach the process. And then we have this Docker container running here, and I'll just attach it. Okay, now I am in Docker container. Again, let's make sure if the GPU driver is being recognized by this container, do the same thing, NVIDIA, SMI, and it works the same because the NVIDIA Docker toolkit. Now, the real fast try that you can do is just Python main _ real-time time the pi, and then it will just read all this data if you have the path in the correct data set and so on. And then it will just take a few minutes to few seconds to read all this image data, and then I will try to run that. And then if I just go to main _ real.py, realtime.py, and this is the code that runs all this in real time. And if you need to deep dive in, please read the code from top to bottom. That's easy to say, but yeah, that's it. And then if you want me to go over the code line by line, please comment down below or open a discussion in the Git repo so that I can go over a little deeper. And then that's it. So these two are the input images, standardized input images, and then in real time is plotting the movement of the camera in real time. However, with this plotting, the frame rate is really slow, between 2 and 5 Hz at best. And that's because of this matplotlib plotting function here. This is really slow. And then if you don't like that, just uncomment all this plotting part. And then run that again. It's going to take, again, a few seconds to read all these image data set. And it'll just run this. And then after running all this, it'll plot again for entire estimated path and ego motion of the camera after running all this batch by batch. And then this is running in real time. That's because it's relying on the weight vector that I have created in waste folder here. And then as you can see, this frequency is faster than before. Instead of 5 Hz, it's 60 Hz. So I'm satisfied with this result. But the caveat of this thing is that you can't plot it in real time to have this frame rate. And then in practice, really, you don't need any of these visuals for humans because it's for the robots. Anyway, that's the kind of brief introduction how you can run this really quick. Now, for now, let's stop it. And then again, like I said, if you have any questions, comment down below. Also, you feel free to open these discussions or create new discussions or issues about this project. And then wave vectors here. So I have uploaded all these wave vectors in this link. Just not this link. This link. Just open this up, download, and then unzip all this .pt file underneath this folder. Then this code should be able to just automatically read all these wave vectors and then run this file. And if you don't have any GPU, no RAM capacity, actually my computer is running on 128 gigabytes. So if you don't have that, you don't have to have it to read all this data. It depends on how many sequences you need to read. But anyways, if you don't want that, or if you just want to see the result only, then you can just run this plot all pi. And that's because I have just created all data and saved it as a text file. So you don't need to run any algorithm. You're just plotting all this data in this file. So if I just want to run this code, I'll just go to results folder, clear all that, and then I'll run python plot all.py. And then if you have this kind of annoying thing, that's because of the path of this container of the Python path is messed up. If I go here, I have this thing. Just copy paste, and then run again. Plot all.py, and it should be running. If not running, frag that. Just open up a new terminal, run that again in Python. No, I gotta get into see the result first. Then Python plot all.py. That should be running. It looks like it is running. Okay, great. Figure 1 and figure 2, figure 3, and a lot of figures are coming out, and that's the result that I'm talking about. So let me go over this result really quick for now. So let's go over to figure 1 first, and that's the delta U, and that's the displacement between frame and frame, but not real nonlinear displacement that I'm talking about. What I mean by that, so if you remember from the presentation, this one, this du is this one, u. And although your robot has moved from 0,0 to 0,1, the du is not really 0,1. It's in between, like 45 degrees. And then the rest of the work is done by this rotational movement, which is omega here. And then this is the du, and that's the d omega. And then the final actual frame-to-frame movement is the translation. As you can see, if I compare all, the red is the ground truth, and then these blue dots are predicted du by the convolutional neural network. And then these blues are like 1 sigma of the du, which is coming from the covariance matrix. Again, this covariance matrix is built by the output of the Cholesky decomposition of the covariance matrix by the neural network. And then same for the omega and here. And then finally, after calculating this part, the translation with omega and then du all together, then we have the translational movement. It's like this. And then if I just map all this into ground frame and then integrate, it's going to be like this. So this is x, y, z movement through time. This is a position. So ground truth position is this, and then this is y movement and z movement. And the interesting thing is the covariance is being added through time, and then the x-axis case is really worse because the drift is even larger than the, I think it's 3 sigma of this covariance, and the ground truth is not even being covered by this uncertainty. However, when it comes to z-axis, it's good because the ground truth is covered by, I think, 6 sigma or 3 sigma of all these uncertainties. In a way, this prediction is quite reliable. And then if I plot this x, z, y is just a different axis, not really x and y. So if I just plot x and z, this is top view, and then the circles are the covariance, uncertainty. So if I zoom in, the car starts from 0,0, and then as the car or the car camera moves forward, this covariance also grows with this as the path goes. And then, yeah, the uncertainty ellipses are growing as the car moves forward. And then after that, I'm just plotting all these same covariance ellipses or uncertainty or standard deviation ellipses are keep growing as it goes. I'm just sparsely drawing all these ellipses because if there's too many, it's just too messy graph, right? So that's why I'm just refraining this drawing thing by stepping by 500 data points and so on. And then at the end, this ellipsis is the largest. And that makes sense because this uncertainty grows up to the end. So that's this first graph. And then this is not really corrected by Kalman filter. Yeah, this is only the output of the convolutional neural network. So let me close all that for now. And then next thing is that's the quick plotting or running the code on your site so you can test it. And then if you want to see how this main_cnn.py works, you can always run this. And I turned on test only as true, and it's going to ignore run train part. If you run train, it's going to just replace this wave vector. Keep that in mind. And then you can always run this as well, and Python main dot. And then I will start reading the images from the beginning again. And it's going to take a little bit longer. That's because I'm reading sequence 0 to 4. And just in case if you're wondering what is this sequence, it means there are like 21 sequences, and then each sequence has all these image folders like this. And then each image folder, there is sequence like the index of the image. And then if I keep clicking right button, it moves forward as if it's playing the video. And then if I just keep pressing my right arrow of the keyboard, then I'll just playing the video like this. But it's, as you can see, the image index, the file name keeps increasing. So that's the image index number. And then this is the number of the sequence that I'm talking about. So to train, this is reading all these sequence of these images from the KITI dataset. And then sequence range is 0 to 11. That's for the test dataset. It's really large data, and then it's as long as it works, it's just going to work. For now, let me stop it, because just getting this thing work on your side is the purpose of this video. So let me keep going. And then if you want to see the result of our training and the test part of the Kalman filter optimization, you can also refer to this file main_kf. And then simply this code is just reading all the data set, the result data from the CNN, and then it reads all that, and then again goes through all this Kalman filter optimization thing. And then how the code is working. Actually, let me run this first, main kf.py. That's just going to run this for the first data set, and then that's the result of after the Kalman filter. As you can see, this red signal is the ground truth of the position for x, y, z. And then as you can see, blue is the only CNN output, and green is after the Kalman filter of this blue. As you can see, it's much smoother than blue, the raw output of the CNN. That's the result of the Kalman filter, and I like this in a way. Although it's not really perfect like this, but that's still way better than this raw output of the CNN. Then if I see the z-axis like this, let me increase this a little bit, and then let me zoom here. It's really smoother than the blue output. And then if I just integrate all this green, which is the Kalman filter output, is way better than this line for z-axis. But for x-axis, not much. Sometimes works, sometimes doesn't work. It means we still lack the number of data to train. That's one of the limitation of this approach of this visual odometry, because we need more data. And then if I just plot all these paths as a top view, and overall it's pretty good and quite better than this blue signal, which is just the raw output of the CNN. And then as you can see, we have corrected the z-axis as much as possible. No, it's not the position, like this. As you can see, this z-axis, the vertical axis of the pattern, is quite aligned way better than the blue one, but when it comes to x-axis, it didn't really correct too much. So that's why the pattern is still quite to the blue signal compared to the ground truth signal here. So that's the Kalman filter correction of this. And then I'm not sure if I mentioned this in previous way. Again, this algorithm really depends on the number of data and the quality of the data. That's the limitation of this deep learning approach. But hey, who knows? Just like ChatGPT made through, if we have a lot of cash to pay the server fee and then data set, then yeah, I think this might work as well. It's just a matter of the data set, and then number of the data set and the quality. So that's the main KF, CNN, and so on. That's how you can run this. That's that. So if you want to go down a little deeper of this code, you can just divide by main CNN KF real time. And then a data reader has two parts. One is CNN and KF. CNN data set is just like this. Just this file has only algorithm for reading the data. For example, if I just go down to get images, it has thread, and then in each thread, I'm reading the images from a certain number of the index of the image to a certain number, end of the index. So I can read multiple images at the same time. And then if you want to see this algorithm only, it has a main routine in this file. You can just run this file independently. And then if I go to prep-data.py, what it does is just standardizing the images and other data set, so that it's more helpful for the training process to converge faster. And again, this one has its own independent main routine. If you want to test, you can just run this file independently. And then video data set is more like a data loader for PyTorch. And then it's just dividing the validation set, training set, and test set. And then it just returns the right sort of data set during the training and test algorithm. And same here, it has its own main routine. You can just test it by yourself. if you need to deep dive into this project. Also, same for the Kalman filter. Only difference is that Kalman filter here doesn't really read the images, I believe. That's because it just relies on the output of the CNN data, which is saved in the result data, and then it just read the output of the CNN and then processes all this Kalman filter optimization here. But anyway, this is only the reading part of the data. Again, I put the separate main function here. You can just deep dive if you wish. And same thing, prep data is for the standardization, and VO data set is for dividing the test set, train set, validation set as well. So that's the data reader part. And then if I go to the models, I have filter model. For example, if I just click the Kalman filter model, the pi, this is just a simple PyTorch implementation of the Kalman filter. For example, I'm just calculating a Kalman gain using PyTorch inverse and matrix multiplication. And then it's just calculating the error after all Kalman filter algorithm. And then if this error throughout all data set is large, and then it based on the loss of this feed-forward network, and we'll just gradient descent for this loss function. And then KF block is just simply the same thing. It's just implemented in the NumPy. And then it's just more like a testing the output of this Kalman filter algorithm. And then again, all these are called from main_KF. And then this is algorithm for if it is training, for example, it goes through this part. If it is not training, it just goes through this part. KF NumPy is block here, and if it's training, it's calling where it's something like KF optimization somewhere here in the model. So this KF is the KF model here using PyTorch. I'm just using different implementation of the Kalman filter, either NumPy or PyTorch based on training or test. That's it. And then the rest of them is more sorting out or manufacturing the data set, like standardization and then right index and so on. And same for the CNN model as well. The main model is implemented in model_CNN_0, and it calls all these model fully connected layers and this convolutional neural network in 2D block. And these are just another implementation in my own PyTorch API algorithm. And this is just a function or class using PyTorch neural network model. And then I'm just using the dropout as magic number. Maybe I should have, I can update this one as another parameter that I can configure later on. But anyway, that's the point. The convolutional 2D block is just another just stacked up convolutional neural network using PyTorch. And then all these CNN fully connected layer is in this file, CNN model, CNN FC, and then these are just like a bunch of other multi-layer perceptron, fully connected layer, and so on with these activation functions. And then same thing. And then one thing that I need to mention is this one, batch 33 met fact 3 mol. This is not real neural network, but it's instead more like a matrix operation in PyTorch. What matrix operation is this part? This kind of matrix operation is implemented in PyTorch, or also building the covariance matrix from the Cholesky decomposition of the output from the neural network. So that's the model is going. And then I think that's it. And then what the real time does is that it doesn't rely on this predefined output data. Instead, it's just literally read all this data, input data, and then it creates the neural network model and then loads all these weight factors. And then it creates data holder so that I can save all this output of each iteration into here so that later I can plot all this. And then what it does is literally process the model like feed forward network, and then with this input, and this is the output of the convolutional neural network. Instead of saving this data, I'll just use this data directly to here. And this part is just converting all this PyTorch GPU data into a CPU version so I can use it in NumPy. And then this is just a Kalman filter implementation using NumPy. And then I'm just saving all this data into this placeholder of the data so I can plot all this later on. That's how this real-time example is implemented. And then again, if you have any questions, please do comment down below. And then also please leave any comments or discussion on this GitHub project as well. So I think that's it so far. I'm Elliot. Thank you for watching this video, and I'll see you in the next video. Thank you.